We'll be looking at question 20, June 2022. This question is about equilibria involving hydrogen. Hydrogen is used industrially to make ammonia. You have the equation here, as in the Haber process. You got the enthalpy change. Now, this is it wants us to determine the equilibrium constant and explain why the operational cost conditions used by industry may be different from those required for maximum equilibrium yield. So this is a question of why is optimal conditions not used and a compromise used. So we discussed those points. To determine the Kc value, we need to use this data, the information given. So got 1.20 moles of nitrogen reacts with this 3.60 moles of hydrogen in a container. The mixture is heated with an iron catalyst and is allowed to reach equilibrium. And at equilibrium, it contains this much ammonia. So what we do, the mark scheme just shows you calculations, but as you remember in class, we use the ICE table. The ICE table for a question like this is very helpful because it gives you a nice visual. So initial, change, and at equilibrium. So write these down, initial, change, and at equilibrium. So initially, what we've got is 1.20 moles of nitrogen and 3.60 moles of hydrogen. We got zero product at the moment. At equilibrium, it tells us that we have 1.60 moles of ammonia at equilibrium. That means it has gained 1.60 moles of ammonia, and you can see it's a 2-to-1 ratio to nitrogen. So that means half of that, so 0.80 moles of nitrogen have been used up. Nitrogen and hydrogen react in a 1-to-3 ratio. So that means 0.80 multiplied by 3 is 2.40. So these are going to get used up. And this much ammonia is produced. And so at equilibrium, you got 1.2, take away 0.8, 0.40. You've got 0. What is that? You've got 1.20 moles of hydrogen left. Now, these are the moles at equilibrium, but we need to work out the concentration. And the concentration is given in the question as 8 decimeters cubed. So we divide all of these by 8. So the concentrations at equilibrium are as follows. 0.4 divided by 8. That's 0.05. 0.15. 0.20 moles per decimeter cubed. What we then work out, we give the expression of Kc, which we're trying to work out. It's products over reactants. So ammonia, we raise the power, the big number to the power, nitrogen, multiplied by hydrogen, and the 3 is raised to the power. What we then do, plug in these values, 0.20 squared over 0.05 multiplied by 0.15 cubed. Let's see what this gives us. I've done a wrong calculation here somewhere. And where is that wrong calculation? What have I read wrong here? 0.16. Ah, apologies. You see, 0.160. 0.160. So this gives us 0.160. Bear with me, ladies and gentlemen. Let me just redo these. Let me just recalculate these. Okay. At equilibrium, you got 0.160. That's formed. That means you have gained 0.160 during the change. It's a 2-to-1 ratio to nitrogen. That means 0.08 moles of nitrogen has reacted, and multiplied by that by 3, that much moles of hydrogen has reacted. At equilibrium, this will give you 1.12. This will give you 3.36. And we then divide these by 8, which is the total volume. And it then calculates our concentrations. There you go. Moles per decimeter cubed. And then we just plug these values in. So that gives us 0.02 squared divided by 0.14 multiplied by 0.42 cubed. That's better. That gives us, KC gives us 0.03. How many sig figs? It doesn't say. We'll do 386. And the units for this, let's see what the units are. You've got concentration divided by concentration squared divided by concentration to the power of 4. If you combine them together, That means that cancels out and you're left with a squared. That means you'll have mole divided by mole squared and dm minus 6. So if you're dividing by mole squared, that becomes a -2, and a minus 6 becomes a 6. You have your Kc value, you've got your units, and that has the potential to give up to about 4 marks out of the 6. It's asking about why the operational conditions may be used in industry may be different from those required for maximum yield of ammonia. Now you see, for temperature, for maximum yield is low temperature. Why? Because the forward reaction is exothermic, as shown in the question over here. Now it's exothermic, but in industry, we will use a higher temperature and the reason for this is to give higher rate. You don't want a great yield, but it's produced too slowly. As for pressure, high pressure used. Why? As fewer moles of gas on right-hand side. It's a bit of Le Chatelier's principle. If we increase the pressure, the equilibrium will shift to the right-hand side to oppose that change in increased pressure, because the right-hand side has fewer moles of gas, which will counteract the increase in pressure. However, why would extremely high pressure not be used? Now, the dangers are with extremely high pressure is, it's expensive. And also, it's a safety hazard. So these are pros and cons of things to be kept mindful of in industrial processes. For example, making ammonia. Now, as for the catalyst, in the question, you'll notice that you got an iron catalyst. Now, what's the benefits of using a catalyst? Because it speeds up the reaction without getting used. It allows lower temperatures to be used. Which will reduce fuel expenses. And as you know, catalysts, they speed up the reaction as well. So increases rate. Quite a big question there. Points for your consideration. Moving on. You got another separate sort of question here on equilibria. It says when the temperature is decreased, the value of Kp decreases. When the temperature is decreased, the value of Kp. Now, Kp is to do with partial pressures. And it's going to be products over reactants, but we will not use the solids. We will only use the gases. Solids and liquids are not used in a Kp expression. So in this case, it will be H2O. So let's write down the expression, the partial pressure of H2O, and there's a big 4 there, over the partial pressure of H2, which there is also a 4 there. These 4. And it says here, when temperature is decreased, Kp decreases. When temperature is decreased, Kp decreases. That means that the partial pressure of water is decreasing and the partial pressure of hydrogen is increasing. That means less water is produced, water decreases and the hydrogen increases. That means the equilibrium is shifting to the left at decreased temperature. That means if you lower the temperature, is to oppose that change, it's going to go in the exothermic direction. So the reverse reaction is exothermic, but the forward reaction will be endothermic. I'll just repeat what I said. Because at decreasing the temperature, the Kp decreases. It tells you in the question. A lowering of Kp means the amount of water is decreased and the amount of hydrogen is increased. That means the equilibrium has shifted to the left. The left or the reverse reaction must be exothermic to oppose that temperature decrease. So the reverse reaction is exothermic. The forward reaction must be endothermic. And what does the mark scheme say? Endothermic. Reaction is endothermic as equilibrium shifts towards the left. 2 points for that 1 mark. This is an interesting question. 2 students are discussing the effect of pressure. Student 1 says there are more moles of products than reactants, so increasing the pressure will shift the equilibrium to the left-hand side. Student 2 disagrees. Determine which student is correct. You see, with pressure, we are only focused on the gases. And there's 4 moles on each side. If you were to, whether you increase or decrease the pressure, it will make no effect on the equilibrium position because there are same number of moles of gases on each side. So student 2 is correct. And why is student 2 correct? Because there are the same number of moles of gases on both sides. Interesting question. That's the end of that question. Thank you. I'll see you next time.